Hey guys, welcome to Help with Homework with your host, Dr. Neutron. Let's take a look at problem 21 in the homework. It's a good one. Okay. So it's important to remember that in this problem, we are looking at the force between these different particles. And that is a key point here. Right? And right here, particles 1 and 2, those particles do not move. They are fixed. Okay? And so during the problem, we only move particle 3. Okay? So particle 3 is the only one that moves. And when particle 3 moves, the net force on particle 2 is going to change, because as particle 3 gets farther and farther away, its force, the force that the other two particles experience, are going to decrease and decrease, because the force decreases as a function of distance. Okay, now this plot here, it asymptotically, it says the net force on particle 2 asymptotically approaches 2.123 times 10 to the minus 25 newtons. Okay, so what does that mean exactly? Physically, what is going on? Well, you should think about it like this. Okay, right here at this place where the force equals 0, that's a very special position, and we need to understand very clearly what's happening in the problem, because at that position, it's critical to understand what's going on. Because what's confusing about this problem, what was confusing to me is, well, I didn't read the problem carefully, and sometimes when I read things and I'm on video, I don't know, the circuits, the little LEDs, or the brain RAM doesn't boot up properly. Okay, but now that I had time to think about it in a quiet place, I can tell you what's going on. So always remember that if you can't figure out a problem at first, that doesn't mean you're not good at physics. Okay, because a lot of physicists, when you read it in 2 minutes, you don't always understand it. So don't feel bad. Don't say, "Oh, I'm not good at physics." No, it doesn't mean it. It just means that these are good problems. You're gonna have to think about things, just like in life. You're gonna have some trouble. Okay, I'll tell you that. You don't always know what the solution is. Sometimes it takes a while to figure it out. Whatever it is, you can work it out. Just don't give up. So there's my motivational talk with Dr. Neutron. Don't give up. All right, back to the problem. So the important point here is that 1 and 2 don't change. And what this graph is really telling you is, what is the force on 2 when 3 has gone to infinity? Okay? Because then you can just say, all right, F2 equals K times Q1 times Q2 over R squared. Okay? Now, how do we get R squared? Because that's really the key here. That's the key element. If you understand that, it's the key to unlocking this problem, which is what I didn't think about yesterday, but now I thought about it. Thank you for explaining that to me, Tabby. That was very helpful. Okay, so really what you have to do is you have to say, okay, let me switch to my DocuCam, or maybe the theoretical physics cam. Yes, oh no, not that one. There it is. Okay, so you can see my face. All right. Okay, let's move this down a little bit. Yes. There we go. All right, so what we need to figure out is particle 1. Oh, wait, is that particle 1? Don't mix up the numbers. It makes it harder. Particle 1 is here. Particle 2 is over here. And particle 3 starts out here. Okay. and it goes to infinity. Does it ever get there? But does anything ever get anywhere? Let's say you fire this pin at my head. Okay, think about this. Do things ever get anywhere? I don't know. The pin travels half the distance to my head. It travels half of that distance, and it always has to travel half of the distance. Okay? So, if it's always traveling half the distance, then it never actually hits my head. Oh my goodness. It just went through my head. Never actually got there. Don't you understand? The particles never actually get there. Zeno's paradox. Think about it. Okay, back to our particles. It goes, we'll say, close to infinity. I mean, where is infinity? Can you ever get to infinity? Is it the edge of our universe? Is there even an edge to the universe? Or is everything stored on the surface of the edge of our universe? I don't know. We'll just say it's headed towards infinity. It doesn't get there, but it's really close to infinity. That makes math people sleep better at night, I think. Okay, so as this particle goes to infinity, what force are we left with here? Well, our plot asymptotically approaches a specific value for force. We know the force is 0 at this point here. This is 0. Okay. So, how could it be 0 there? That must mean that at this point right here, the system is in equilibrium. Okay? So, at where it goes to 0, where the force goes to 0, that's equilibrium. That's the key to this problem. Once the particle's at equilibrium, we can get a distance because we know that at our distance here, that's how far apart particles 1 and 2 are. Okay? So at r equals where the force equals 0, at that value, that is our equilibrium position, and the problem tells us where that is. Okay, so here's our plot. Okay, and it is drawn something like this. Okay, so we've got this value here, and if we read the problem carefully, which I did not yesterday, it tells us that that distance, or the scale of our plot, so right here, this whole thing, the scale of it, xs, is equal to 1 meter. Okay? That means that equilibrium, for the numbers that I have in mind, equilibrium is at 0.5 meters. Okay? So that's the distance between particles 1 and 2. Now, that's when this is at 0, there's 0 force. But then if we take particle 3 away and we go off towards infinity, not to infinity, then that particle's gone. There's no more forces left. So we have to say, well, what is our force? Well, when this goes to infinity, that's the force between particles 1 and 2. That hasn't changed, okay? What did change was the force from particle 3. But remember, forces add together, and when they add together and they equal 0, then that's equilibrium. But if now the force from particle 3 has gone to 0 and we get this value, that's the value of our force. Okay, so just watch the video again and try and think about through that. Okay, because that's really the key. So this really isn't, because we know the physics that we're going to be using. Okay, it's F equals K times Q1 times Q2 over R squared. Okay, that's the physics, but the authors are really into also making you think logically about the problem. Okay, so maybe that's what you also learn from this this class, is how to analytically think about the problem. That's one of the rubrics in the syllabus. Okay, so we know then that this we know what our equation is. F equals K times Q1 times Q2 over R squared. We know what R squared is. R squared on my for my numbers is just R equals 0.5 meters. Half that distance right there. Okay. Then we know what K is. Okay. And we know what Q1 One is, we don't know the sign unless we also think about it, okay? So we know that particle 3, what did it say particle 3 was? I think particle 3 is positive, okay? So particle 3 is positive. So if we look at our plot here, okay, if this one's positive, if this one was also negative, this thing could never be at equilibrium. So let me just look here real quick. And let me make sure I'm not leading you astray. Okay, yeah, so if this one is positive, this one also has to be positive as well. It could not be in equilibrium. If this one was negative and this was positive, it would push it into it. It could never be at equilibrium. So we need something here that keeps the particle balanced. So that means Q1 has to be positive, and it has to be the same as particle 3. So my Q3 was 10e. Then Q1 is also positive 10e. F net, okay, F2 net. Oh, and am I even showing that? Am I even writing on the screen? No, I'm not. So, all right. Oh, I need to move my big snout out of the way. Q3 is positive 10e, and Q1 is also positive 10e. Has to be positive because we have to be in equilibrium. Now, we know what F is. Looking at our plot here, it tells us in the problem that we asymptotically are approaching 2.123 times 10 to the minus 25 newtons. So that's how you do problem 21. I'm not going to have you watch me type it into Mathematica. You can see the answer on the screen, or you did earlier. Maybe go back, rewind it. Okay, that's it for problem 21. You should be able to maybe do it now. I think you can. I believe in you. Thanks for watching, and I will be posting more videos as soon as I can.
Thank you. Like and subscribe down below.